Whenever I enter that lecture, I don't want to learn about history. Take me on a biochem adventure. Without it, life would be a mystery. The 20 amino acids make up our DNA. The H2O Haten group of nonpolars got alanine, glycine, isoleucine, leucine, methionine, proline, and valine. Then you got the polar groups that love that H2O. Asparagine, cysteine, glutamine, serine, threonine. Those circle-forming aminos like phenylalanine, tryptophan, and tyrosine. The last aminos to talk about are arginine, histamine, and lysine. Got that positive charge. And aspartate and glutamate with the negative charge. They link themselves together by a peptide bond. Through a condensation reaction, acidic or basic features can be put into action. Whenever I enter that lecture, I don't want to learn about history. Take me on a biochem adventure. Without it, life would be a mystery. What we are without proteins, the primary structure gives the central dogma of biology. It starts as DNA that transcribes to RNA that translate to proteins. The secondary is known for its beta sheets and alpha helices that have those strong hydrogen bonds and fine site angles. The alpha helix rotates clockwise and has a helix dipole. Negatively charged amino acids near the terminal stabilize where positively charged destabilize. Look for it in alpha keratin of hair and nails. The beta sheet runs parallel and anti-parallel where hydrogen bonds form. It's found in silk fibruin by spiders. Motif is known as the folding pattern with two or more elements of secondary structure. Hairpins, crossovers, and beta-alpha loop are examples. Hairpins connect those anti-parallel beta strands while crossovers connect those parallel beta strands. But the beta-alpha loop is where the alpha helix connects two parallel beta strands. Tertiary structure is made from ionic, covalent, and H bonds. It has the interactions between alpha helices, beta sheets, and beta turns. That quaternary structures has peptide chains on chains on chains. We're not done with proteins yet. The globular proteins have alpha helices and beta sheets like myoglobin, where the interior is hydrophobic and exterior is hydrophilic. But to maintain that folded state, hydrogen bonds and ionic interactions are displayed. When there's too much heat or salt, proteins fall apart. Whenever I enter that lecture, I don't want to learn about history. Take me on a biochem adventure. Without it, life would be a mystery. Enzymes make reactions go faster by lowering that activation energy. Sometimes there are inhibitors that try to stop reactions. The competitor enzyme completes with the substrates to bind at the active site. The uncompetitive enzyme binds to the ES complex, unlike the mixed inhibitor that can bind to S or ES complex. Let me tell you about hydrolytic cleavage of peptide by chymotrypsin, which is the pathway of enzymatic reactions. First is the binding of the substrate. Histidine activates serine for nucleophilic attack, where those H bonds stabilize that negative oxygen to break apart that peptide bond to give you the axle enzyme, to only get attacked by H2O to form another intermediate. That deadly acid catalyst breaks the covalent bond to let it be free to disassociate. Whenever I enter that lecture, I don't want to learn about history. Take me on a biochem adventure. Without it, life would be a mystery. Hemoglobin is what allows us to still be alive. It's a type of quaternary structure that thrives. Hemoglobin has alpha 1 and 2 and beta 1 and 2. They start to form hydrophobic interactions. The strongest of those are alpha 1 and beta 2, or alpha 2 and beta 1. Oxygen comes from the lungs where the partial pressure is 13.3 kilopascals and runs to our tissues where the partial pressure is 4 kilopascals. Hemoglobin starts in the lungs saturated at 98%, and when it moves to the tissues, its saturation drops to 32%. When oxygen binds to hemoglobin, it causes a conformation change, going from its T state where it lacks some oxygen to its R state where it's fully oxygenated. In summary, it's going from its tense state to its relaxed state. Now the Bohr effect can be one of two ways, where O2 is high and CO2 is low in the lungs, therefore the pH is higher. This increases the affinity of hemoglobin for oxygen, or where O2 is low and CO2 is high in the tissues, resulting in a lower pH. That decreases the affinity of hemoglobin for oxygen. You ask how you regulate hemoglobin affinity of oxygen, and the answer is 2,3-BPG regulates. It binds at a distant site from the oxygen to make sure the O2 gets to the tissues. Hemoglobin has that cooperative attitude. You better express some hemoglobin gratitude. Whenever I enter that lecture, I don't want to learn about history. Take me on a biochem adventure. Without it, life would be a mystery.